Hello and good morning, everyone. Hopefully everyone can hear me okay. Thank you so much for joining us this morning for our first of our webinar series, which is focused on nature-inspired construction. We're so pleased to have so many of you join us this morning. We've got a really exciting lineup this morning as well. Just want to run through a couple of quick things first of all, just on a housekeeping point of view. Due to the large number of people that are registered this morning, all participants will be muted. So after testing your speakers, make sure you do connect using audio by using the join audio button at the left of the screen, or dial in using your phone. If you do have any technical problems at all this morning, then please use the chat box and our host Pinam will be able to help with any questions you might have. Throughout the session, if you do have any questions for myself or any of the speakers on their presentations, then please use the Q&A function or box at the bottom of the screen. This is just a really great way to be able to put down your questions just as the presentations are going on. Myself and my colleague George will be helping kind of pull those questions together, and we'll be feeding those to the speakers during the Q&A section at the end of this session. If one of your questions is for a speaker in particular, then please just note that down as well, so we make sure that we ask the right person around your question. Just also note that the webinar is being recorded this morning. We will be circulating this through our newsletter and also be made available on the KTN website. So just to start off, I haven't actually introduced myself yet, but I'm McKenna. I'm the Knowledge Transfer Manager for Emerging Technologies Industries at the KTN, and I do lead on our Nature Inspired Solutions SIG, which I'll be telling you a little bit more about at the end of the webinar session this morning. I will be chairing the session today, so I'm really excited to be joined by two great speakers, Ehab and Martyn. Just before we get into kind of the swing of things with the presentations, I did just want to run through the agenda. We'll just do a very quick welcome. Went through some of the housekeeping, and I'll do a bit of an intro to kind of set the scene for the webinar session this morning. Followed by that, we will be having our first speaker, Ehab Sayed from Biome, talk about how nature can inspire us to revolutionize the built environment. Followed by that, at 11:25, we will have Martyn Dade-Robertson from the Hub for Biotechnology for the Built Environment and Professor from Newcastle University, talk through living construction and how biotechnology can play a role in the built environment. At the end, we will have plenty of time for questions, so please do kind of jot those down, as I said, in the Q&A box. Myself and my colleague George will be picking those up throughout. And at the end, we'll just do a quick summary and close the session. At this point, we'll let you know more about ways in which you can kind of get involved in the special interest group that we run, and also about some more of the sessions that we've got coming up in our webinar series over the summer as well. So, and also as well as that, we are aware that kind of having events at the moment physically is not something that we can do. And we know one of the great things from having events is being able to meet and connect with other people as well. And so we still want that kind of conversation to happen. So hopefully, you should have received a link to our app called Meeting Mojo, which allows you to link up and connect with other attendees from the session today. If you haven't received that link, then we will pop it as well into the chat box. So you can sign up and book one-to-one meetings, kind of 10-minute slots with other attendees to kind of continue the conversation around nature-inspired solutions and construction as well this morning. So that will run from 1:30 to 4 o'clock. So after this session, you've got plenty of time to go grab lunch or a cup of coffee and then get logged on and kind of have a call or catch up with anyone else that's been involved today. So, but we'll pop the link in just in case you haven't received that. So I think that's kind of all of the instructions. I'm just going to take a quick check and make sure that I haven't missed anything in the chat box here. Okay. Great. So I think that's everything then. So just to get started then, we know that some of you might be joining us today because nature-inspired solutions is perhaps your background. and you're really keen to explore how this might be applied to construction. Or alternatively, you might be joining from the construction sector and really intrigued as to how nature can have a role in inspiring the transformation of construction. So depending on your background, we just kind of wanted to give you a little bit of an overview of what we mean. So what is nature inspired? So what we mean by this is, rather than imitating the whole plant, animal, or biological process, nature inspired solutions aims to uncover the underlying mechanisms and apply them in the design of new products, processes, or systems in a structured way. So the reason why that's a really important thing to look at, but why is it we want to look at nature? And I think kind of, looking at nature throughout kind of the history of time, nature always kind of finds some of the most efficient ways in which it can do things, or the way it's designed or kind of evolved over time, whether that's the way in which animals or birds might move, whether it's ways in which they could insulate themselves or perhaps pollinate. So looking at kind of how those mechanisms work within nature, how can we take that and apply it in, I suppose, the things that we do within our world? Because I think if we're being honest with ourselves, sometimes humans don't always find the most efficient ways of doing things, and we certainly don't always do them in harmony with our local environment. So what we want to be able to look at is how nature's been able to do that, and see if we can inspire solutions for problems and challenges that we're looking at within various different sectors. And that sector we're looking at today then is construction. So the reason why we are looking at construction is because we know that the industrial strategy has been around for a little while, and we looked at kind of some of the key challenges that come out of that, including clean growth and also the huge opportunity around transforming the construction sector in the UK. And the government has set out really ambitious vision for the sector, particularly around halving the energy use of new buildings by 2030, delivering new assets quicker at a much lower cost, and also looking at how those assets operate so that they're done in a much smarter and safer way, and also as well as that with much lower emissions. So there is really no one solution fits all when we're trying to solve such large kind of sectorial and industrial challenges like this. So what we wanted to be able to do today is explore different methodologies and approaches that might be taken to look at that. And with that in mind, we want to look at kind of how nature perhaps can inspire better construction. So without further ado, and without me kind of going on and kind of taking up too much of your time, I want to pass you on to now our first speaker, Ehab. I'm really excited to actually introduce Ehab. Ehab is the founder of a company called Biome, where he's the director of innovation. He's also a PhD researcher, and Ehab was one of the very first, I think, businesses that I actually got to meet that has, I suppose, circular economy at the center of what it does, and is very much around kind of looking at how it can, I suppose, drive innovation in a way that has a positive impact. And that's really kind of at the heart and soul of the business. And so it's been really exciting, actually, since I met Ehab a couple of years ago, to see the business kind of grow from just himself to kind of now a full team, and now to be at the stage of kind of doing their first serious crowd fund. So really, really exciting. So Ehab, I'm just going to pass it on to you now to launch your presentation. And yeah, you've got 15 minutes.
Perfect. Thank you very much for that introduction, Emma. And welcome everyone. Thank you all for joining this really interesting webinar. I think it's really the perfect time to have this kind of conversation. So just sharing my screen. Is that all good? Yep. Okay. So today, I'd like to talk about how nature can inspire us all to revolutionize the built environment. But first, I think it is fair to say that we are all currently living through unprecedented times. The world had to switch gears overnight, and we all found ourselves sitting at home, reflecting, reassessing, and reevaluating, making us collectively and critically question our consumption habits, our production practices, and the way we do business. We look around us and we see that we have entered a new epoch in Earth's history, one that's characterized by the indelible mark that we've left upon the geology of the Earth, as well as the onset of the 6th great extinction. This has become known as the Anthropocene, Whilst we once lived our lives as part of the natural world, the world we've built for ourselves is marked by a form of extraction and consumption that is changing the world around us. The land, the air, the water is saturated with pollution, and the world is hotter than it has been for 120,000 years. The planet's long-term warming trend continues to fuel the fires, freak storms, coastal flooding, and droughts that have devastated communities around the world. With the population of the planet predicted to increase by nearly 40% in the next few decades, the demands placed upon the world have far exceeded a point of sustainability. The construction of our built environment and our infrastructure alone generates over 50% of global greenhouse gas emissions. As an industry, it is also perhaps one of the most wasteful. With that in mind, we have already used over half the world's natural resources to build what we have today. So if the combined infrastructure plans of growing and developing economies are ever to be realized, we will need a further 7 planets worth of resources. In nature, the concept of waste does not exist. Everything is in constant flow, constant circulation, with outputs from one process becoming the inputs for others. So as designers, engineers, architects, project managers, surveyors, as people, if we are going to play creators, then we must take a leaf out of the 4 billion page book that features the civilizations we know today in the last 6,000 pages. Biomimetics is not the simple imitation of natural form, as Emma clearly described just now, but it's the science that is driven by the realization that our most prized inventions exist in more elegant, eco-sensitive, efficient, and effective forms in nature. Bamboo stems and lily pads contain beautifully constructed structures that make man-made architectural beams and struts seem underwhelming. Our air conditioning and ventilation systems cannot compete with the way the architecture of termite mounds passively maintains precise temperatures. A deep understanding of how organisms achieve such feats of engineering can shed light on how we can solve some of the industry's most pressing challenges. And we find that when we rely on biology as opposed to technology when solving a problem, we use much less energy and resources and much more structure and information. And in this age of information where we're collecting data left, right, and center, biomimetics has become a real possibility. And it requires a certain level of systems thinking, where you perceive the world around you as a collection of dynamic, complex systems. Once the outputs of one system become inputs for the same or another system, we have what we now call a circular economy. We are moving away from an extract, make, use, and dispose linear economy, which has a tremendous negative impact on the environment and our health, to one that is circular, where we ethically source, reuse, or recycle existing resources on our economy and consider the environmental, socio-ethical, and economic impact of the material or product's entire life cycle. And that's exactly what we do at Biome. Biome is a research and development-led company that places biological systems at the heart of its inspiration to revolutionize construction and the way we do business. We achieve this through our bio-based materials, construction systems, and a range of services. We are starting with the most tangible and immediate of these offerings, and that's our materials. Orb, or organic refuse biocompound, is a semi-structured sheet material made entirely out of food and agricultural waste and contains a 100% natural binder that we've developed, which is actually edible. That's how natural it is. It is currently available for use in interior architecture and will soon be available for dry lining in buildings. It outperforms other wood-based sheet materials when it comes to mechanical strength, and it is carbon negative, does not contain any synthetic chemicals or toxins or formaldehyde, and is highly price competitive. Orb is currently being developed into a plant-based concrete, which would be a serious game changer. Our plant-based concrete will be available within the next 2 to 3 years. We also work with one of nature's most wondrous organisms, mushrooms. We use the root systems or the vegetative part of a mushroom to consume a variety of organic and synthetic waste, and the outcome is the world's most advanced building insulation materials. We have developed biologically unique species of mycelium, and we have naturally accelerated the revolution to favor particular traits that would improve their mechanical and physical properties, and we train them to consume a variety of waste streams. We are currently testing our mycelium insulation against industry standards, and we've been blown away by how we managed to achieve thermal conductivity values as low as 0.024, which may not mean very much to most people, but it competes with market-leading synthetic insulation, and in some cases, it is 2 to 3 times the thermal insulation value of commonly used alternatives. As you can see in this video, it is naturally fire resistant due to the chitinous nature of mycelium. For VOCs, or volatile organic compounds, which are released by materials throughout their life and affect the indoor air quality and therefore our health and well-being, we achieved the highest possible score of A+, making it one of the healthiest materials available. No additives, no chemicals, outperforming almost all other insulation products on the market by simply using nature's genius. Now, last year, we had an interesting little discovery in our R&D lab, which led us onto a super exciting journey. You may be aware of mycelium's capabilities known as mycoremediation, which is a process by which fungi produces appropriate enzymes that break down complex compounds like plastics into hydrocarbons and carbon dioxide. We have discovered last year that we have developed mycelium strains that are capable of consuming plastic. The rate of degradation that we were able to achieve was quite significant, and that was quite the revelation. Last year, the Onion Collective, a social enterprise at the vanguard of social action and community business, joined forces with Biome, and we were awarded the Waitrose Plan Plastic Prize to continue to develop the research further and ensure that such technologies have a transformational impact on local communities. This has allowed us to carry out numerous experiments over the last year, where we continue to evolve our strains through a non-intrusive and non-GMO process known as directed evolution, which basically mimics the process of natural evolution in an accelerated lab environment. This has resulted in the development of 3 strains that can successfully consume PU, polyurethane, and PE, polyethylene. And you can see in these microscopic images the plastic being surrounded and consumed by the mycelium. Unlike other plastic recycling processes, which can propagate the current plastic crisis, encouraging the production of more plastics, our process eliminates plastic completely, and all outputs, so the non-toxic hydrocarbons, are stored in the resulting mycelium material, which in itself is a replacement for plastic and other damaging materials, and the carbon dioxide is turned back into oxygen through the process of photosynthesis and fed back into our incubation space, providing fresh, oxygen-rich air to the next batch of mycelium, ensuring a completely closed loop in our manufacturing process, resulting in the production facility effectively being a carbon sink. Although our mycelium insulation, which is currently available, is grown on organic substrates, we aim to eventually integrate plastics and other synthetic waste streams from construction, fashion, and other sectors into our production process. Due to the vast environmental benefits and global potential of such technologies, it was essential for us to deliver this to the world in a way that is ethical, equitable, and sensitive to our current economic landscape at a time where it is needed the most. So with the addition of a grant from Power to Change, we are setting up the world's first community-led biomanufacturing facility with the Onion Collective. Apart from being the first large-scale facility to produce mycelium insulation, another unique aspect of this collaboration is in the way it acts as a catalyst for regeneration within a community. Again, taking inspiration from nature, we have developed a business model that allows communities to drive industry in quite a revolutionary way that ensures the regeneration of the local community, environment, and economy. Our first biomanufacturing facility is almost completely built in Watchet, West Somerset, and it will start at a scale of 3,000 square meters of insulation panels as output, so around 20 homes worth per month. And over the next couple of years, will eventually be scaled up to provide enough insulation for 120 homes each month. At that scale, we would be using up around 150 tons of waste and sequestering around 30 tons of carbon each month. It will provide over 30 new local jobs, and through the equitable distribution of profits, provide a constant income for the community, allowing them to invest in their education, infrastructure, and social action projects. Our materials will all be combined eventually to form triagamy, an interlocking construction system that combines all of our materials and is inspired by the molecular structure of carbon. It does not require any permanent binders or fasteners to create robust structures that can be deconstructed at any stage of their life, giving us a real practical solution for circular buildings, and allows architects near limitless flexibility in design, and also means that buildings can shrink and grow in accordance to the communities and the occupants' needs. It reduces a building's environmental impact by up to 120%, build times by around 95%, and costs by 70%. And it's also really important to recognize that nature-inspired technologies and solutions are not only applied to products and technologies, but can also be applied to business models and relational models. By using the way nature intelligently analyzes the world around it to evolve its species, we can actually model the construction industry and the economy around the industry and how it interacts with other sectors in a much more accurate way. We then realize where the stakeholders that are capable of achieving great change in the industry lie, and by activating those stakeholders, you can start a transformation within an industry. So the benefits of nature-inspired solutions span far beyond the application for products or materials or technologies. We're working with some of the top universities in the world. We're also supported by some really big research houses from around the globe, and we're working with some of the top multinationals to really achieve this transformation in industry. We've been awarded and recognized nationally and globally for our work, and we are looking to bring on board as many people as possible and to become part of this bio-revolution. So as Emma mentioned, we've recently launched an equity crowdfunding campaign on Seedrs that allows you to own shares in Biome and be part of this revolution as we grow and scale. So please head to Seedrs, check out our crowdfunding campaign and share it with all of your networks. And we want people to come on board this journey to create a biomimetic future, a future that is not only going to be result in really innovative technologies, but it will help reduce our time and cost requirements. It will help improve our resource and energy efficiency. And it will also allow us to have a seriously positive and regenerative environmental impact at a time of climate crisis. We need to move beyond sustainability and towards restoration and regeneration. And we need to learn from nature to be able to actually achieve that in a cohesive and a holistic way. And it will also allow us to look after our psychological and physiological well-being. And that will hopefully make us a positive and a regenerative part of those last few pages in that book that is known as The Natural World that we're all a big part of. Thank you very much.
Thank you so much, Ehab, for such a wonderful presentation. It was really great to kind of see, I suppose, kind of where it started off in terms of the idea and the concept of this and how it's continued to evolve and now get to the point where you're actually in that process of actually going to be kind of in industrial manufacturing scale. So it's really exciting to kind of see that journey kind of evolve, and even kind of with the pictures and visuals that you accompanied that with, it was really, really great. And I can definitely see there's some questions coming in already for you, kind of, I suppose, on around kind of the commercialization and to reach the scale and bringing that to the market. So we will go into that once we go into the Q&A section. So we can definitely pick that up in a bit. But I am now going to introduce everyone to Martyn Dade-Robertson, who is a professor of emerging technology at the School of Architectural Planning and Landscape at Newcastle University. He is also the co-director of the Hub for Biotechnology in the Built Environment, which is done in collaboration with Northumbria University. Martyn is a really new contact for me anyways, and I actually heard about kind of the hub in one of my first weeks at the KTN, which is only a couple of months ago, around kind of, I suppose, this exciting around kind of two research institutions coming together to explore various different aspects of nature-inspired solutions and bringing together kind of a living construction model as well on site and on campus. So I'm really excited to hear kind of more about this, and I'm going to hand you over to Martyn now to deliver his presentation. So thank you.
Thank you, Emma. So I'm just going to share my screen with this button. That. And I'm going to go to presentation mode. Just check that I can see, so I seem to be live. So thank you so much for the introduction, Emma. And so I have the unenviable task of following Ehab's presentation, which was both brilliantly done and very inspirational. I'm not sure I can hit that level, but we'll do our best. So as Emma mentioned, I'm a Professor of Emerging Technology at Newcastle University, and I'm the co-director, in fact, for a new centre called the Hub for Biotechnology in the Built Environment. So it's a collaboration between both universities. It's funded through Research England, and we got the thing off the ground by putting two research groups together. Over at Northumbria, they have a very strong biotechnology research group. And over at Newcastle, we had architects and engineers who are very interested in biology and have biological experience. So, for example, I'm trained as an architect, but I also have degrees in architectural computing and also synthetic biology as well. So we had this kind of unusual collective, and we decided that by putting our efforts together, we could do something really transformational. So we put a bid into Research England, and we were lucky enough to receive £8 million worth of funding to help us set up. We've been running now for nearly a year. We're in the startup phase very much, and we've got a lot still to do. So much of our money is going to recruit new staff. In fact, we're hiring by next year we'll have 40 staff in total across the two groups, many of them permanent researchers who'll be working in our different research themes. And the other part of the funding really goes to create new facilities. So we had this vision of creating a series of connected facilities, really, that took us from the nanoscale of the microbial world, particularly of microbes, but of really all living cells, and the way that we can engineer and understand and manipulate them right the way up through to the built environment. So we have a series of these staged facilities, the idea being that we can go from the very, very small to the scale that we need for the built environment. What Ehab presented is really incredibly innovative for the building industry. There's very little biotechnology sector in the building industry yet, but we think this is something that's going to change over the next few years. And his is a great example of where we can make quite transformative changes, not only to how the built environment is developed, but to the materials that are used, but all the processes and even the way of thinking about how we construct the built environment. Now, I have very limited time today, so I'm not going to go into all of the themes of the hub, but just to say that we have 4 themes that we work on at the moment that cover a range of things, from the way that buildings are serviced to our interaction actually with our microbiome and the microbial world around us. And I think this is something that we're very conscious of at the moment. There is no doubt that we are living in a period of our history where we're very aware of the microbial environment around us and the effects that it has on our health, and in fact on all aspects now of society. But I'm going to represent today the living construction theme and take you through just a few of the projects, just to give you a little flavour of what we're doing and what we might be interested in doing collaboratively, and how we want to expand the hub over the next couple of years. So we start with a pretty straightforward principle in the living construction theme, that we make use of living materials in the built environment. That much is already fairly clear. We use timber, we use concretes that are based on calcium carbonate from crushed shells and so on. So we already make use of a lot of these materials, but we usually make use of those materials when the materials are dead. And if we were to begin to take control of the process of material making while the materials are living, and even to keep them living beyond as they're used, we could do an awful lot more. We could do some really innovative things in all aspects actually of manufacturing and making, but particularly for the built environment. So there is a huge range of biological materials available with lots of potential benefits. Biology does this kind of alchemy. It can transform one type of material to another with, it seems, relative ease in many different sorts of biological systems. Biological materials are often self-assembling or partially self-assembling, so they do so autonomously through the growth of cells. They are innately responsive to their environment. For their survival, they need to be able to alter their conditions, alter the way they metabolize in their environment, and actually they're constantly responding to environmental conditions in order to grow and to thrive. They can make materials that would be extraordinarily difficult to make using traditional engineering processes at room temperatures and pressures. And we can think about, for example, the ceramic-like materials you see in shell construction, which is a material made at room temperatures and pressures, but has extraordinary complexity in the way it's put together. Living materials can exhibit complex functions, but also living systems create materials with complex functional variations. And so when we want to create complex functionality, we often do so by getting lots of different materials and gluing them together, but often using a single material. A tree, for example, can generate materials of varying functions using basically the same stuff. So you can go from a tree trunk, which is incredibly tough material, is resistant to water ingress and other things, right the way to the tip of a branch, which is flexible, rubbery, and water can flow through it. And using the same basic material that's the same in its chemical composition all the way up. And that we might be able to utilize these processes to make use of waste products from other industries. So we might be able to turn what are considered to be wastes into things that are valuable and have economic benefit and other benefits. There's also a broader question that we're interested in the group, which is to think about the way that these materials are fabricated and assembled. So if we go from a condition in which we think of materials as things that are fabricated and assembled in traditional ways in factories, and move to a system where many other materials are grown, what does that do? And how do we manage that complexity with organisms that are doing things that are independent in some cases of our control? And then there are huge challenges in scaling up. And one of the things that we're most interested in are microbes, which are, well, a microbial cell is about 2 microns across. We have to then use those systems to generate materials that are relevant at the meter or tens of meter scales. And so there are some real significant challenges in scaling that up. So just to give you a couple of highlights really of work that we're doing at the different TRL levels, and a lot of this is very early stage work as we're only just beginning now to explore some of these areas. The HBBE started off with this project, Thinking Soil. So this is an EPSRC funded project. It was developed to imagine, and it was a very moonshot type idea, to imagine a building context in which rather than digging a foundation trench, filling it with concrete and reinforcement and building on top of it, we could engineer a soil that would respond to mechanical loads placed on it by synthesizing a foundation raft, by self-assembling a foundation raft in response to loads. And we started to start that process. What we've been doing is to engineer a type of bacteria that will act as a mechanical sensor. So we've been making a biological mechanical sensor that is also then capable of synthesizing a material in response to those mechanical loads placed on it. So we're in early stages of that, or we've done an awful lot of quite fundamental biological work to understand this. In fact, we're learning new things about microbes that were thought to have been very well understood, but we're learning new things all the time. And we're innovating in fields like synthetic biology to begin to do the first step towards this idea, which is to create a demonstrator of a material that will respond to mechanical loads within our lab environment. And the image you see in the bottom right is a gel that we're using to grow the bacteria, to put loads on it and to test whether it can become resistant or can remodel itself in response to those loads. So that's an example of a project really early in the TRL level where we're having to do some quite fundamental science in order to realize it. And it might not have in the end applications for the building industry. It may well go in all kinds of different directions, but it's a fairly fundamental new piece of biological engineering. This is an example of a slightly higher up work. So what you see here is a video with a hygromorphic material, a material that changes its shape in response to water based on bacteria spores, which are the seed form for certain bacteria. So these are dormant bacteria cells that we then we can lay onto the surface of in this case, it's a latex material. And then as the surface dries, it will cause the material to fold. And we can do this repeatedly effectively. So by putting it in wet and then dry, humid conditions, we can get these little actuators to open and close. And then we can incorporate those into systems at a larger scale. So some of the foundational work has been done in this area. The key papers came from Columbia University, and MIT have also done some work looking at the future of clothing and whether we can use this for fashion applications. And we think that this method might be useful for architectural applications where we want to control humidity, or we want water shape change to be part of the structure of a building. We've just gotten to the point now where we can program the material with relative reliability. We can add different layers to it to give it different response rates. And we've started to explore integrating it with scale-up mechanisms. So in this case, Emily is working with something that's akin to a kind of origami, where we get these actuators being able to fold many different layers and then create larger shape change. And she's just beginning to start working on some more built environment ready prototypes of this work. Another material area we're interested in is nanocellulose. Cellulose is the most abundant biological molecule, complex biological molecule, I should say, in nature. Cellulose is the foundation, but well, the basis of wood, for example. And microbes have their own cellulose forming process. They make a material called nanocellulose, which is really interesting as a sort of an alternative to plastic, or in some instances an alternative to leather. So again, nanocellulose from bacteria is being explored for a whole range of things, from beauty treatments through to high-end music speakers. We think the next phase in the development of nanocellulose as a material is to think about how we can program the material as it's being manufactured. And that involves intervening in the microbial production process through a combination of genetic engineering, but also the creation of novel bioreactors and the integration of digital manufacturing techniques using 3D printing, robotic manufacture, and so on. So one of our PhD students, Sunbin Lee, is beginning to look at how we can create more programmable materials. So looking at possibly creating complex functional composites by getting the bacteria to grow in different ways in different places within our molds or within our systems, and also going into 3 dimensions. So how do we get from a sheet material, and traditionally it's made as a sheet floating on top of a liquid medium, towards something which really has 3-dimensional structure that we can start to use in a meaningful way. And so again, bringing together this understanding of the molecular biology of the cell and the manufacturing context in which this might work opens up all kinds of new possibilities for this kind of material. We're also interested in microbial cements. There are processes where bacteria either create mineral crystals or they induce their formation in their environment. The most obvious one, and in fact one of the founders really of the biotechnology for the built environment commercially, is a company based in the US who have started to utilize microbial processes to make bricks as an alternative cement. The idea being that you can again create a cement that ultimately will give you the same kind of properties as concrete, but at room temperatures and pressures if you can find the right chemical substrate for a microbe to grow. And so we're also exploring this, and we think that one of the reasons why this is not totally revolutionized the concrete industry yet is because there are some real scalability problems to using this process. So while we can create a kind of a range of materials from sandstone to more concrete-like materials depending on your substrate, there are all kinds of challenges of how you begin to cast, for example, a microbial material that is living as you begin to cast it, and also how you optimize the process, how you ensure that the microbes get the right food within the casting chamber, and so on and so forth. So there's a whole set of problems that we think need to be unlocked before we could really start to imagine this as a scalable built environment process. But it's something that we think we can get through to a tipping point where this becomes a really viable building material, and a set of processes that might provide some really interesting building materials as well that might outperform the kind of competitor materials. And then I guess I wanted to sort of go to the higher level. So part of the reason we have the hub is that there are very few, well, I'd say relatively few biotechnologies that are applicable to the built environment yet at the higher TRL levels. And we think that there's certainly a gap at levels 6, 7, and 8. And kind of the R&D work that Ehab and others are doing in this area is trying to make sure that we can get to that point of scalability and industrial relevance. But after setting up the hub, we've put messages out to various networks, and we've started to have questions and ideas come to us that we can facilitate. And I just wanted to focus on a couple of those there. Just in the last month, we've had people talk to us about whether we can use microbial enzymes to modify chitin-based materials, or actually develop new kind of chitin-based materials. These are traditionally that it's done from chitin is extracted from certain kind of sea creatures, the shells of certain kind of sea creatures, and is made into a paste that then becomes a plastic-like material. And whether there is ways we can optimize the enzymatic treatment of those materials to create something which has scalability. A lignification or delignification of woods, so taking softwoods and making them into hardwoods through the addition of lignin, or indeed taking lignin out of woods to selectively alter their properties to make interesting functional timber-like materials. And I had to put in something on mycelium. We've had conversations with NASA in particular, who are interested actually in mycelium and growing mycelium as a building material on Mars. So Ehab, that might be an additional market for you, an emerging market of Martian exploration, because it makes a lot of sense for them to take very little up into space. There's a payload issue, but then to think about what you can construct on site in situ. And actually that sort of thinking is really the sort of thinking we think we need for the built environment as well, a sort of push to a radical vernacular where we make use of the local materials and properties. I just also wanted to say that we have equipment. So one of the things that we're purchasing at the moment is all this new sequencing equipment. Some of it is actually being used to help with the COVID-19 response at the moment, particularly our sequencers. And we're looking to upscale with robotic manufacturing, 3D printing in the next couple of months as things begin to unlock. Just two final points really. At the heart of all this, we want to create an experimental house. And so the meeting I was in before was an always tricky meeting with our estates department to try and persuade them that we should build an experimental living house in the middle of Newcastle University campus. But that is now going ahead, and we have planning permission. We're just about to get planning permission for the groundworks. We're in contract negotiations now. The idea that we'll make this house into a living test bed for these materials, not just for things that we do, but that we're a hub. So we would probably want to go out to Ehab and source some of his materials and use them to test, but also as a demonstrator for the future of the built environment in this regard. So the house will become a kind of exhibition space, a testing domain, and we're looking for partners who might be interested in working with us on that or exhibiting as part of that. As we go. We call it the Ohm, which is a derivative of home, and all of the various omics studies that we're doing, genome, proteome, metabolome, biome, and so on. And I just wanted to say a final thing about it. The great thing about having the group of people together, and we have staff now from molecular biology and computational biology right the way through to textiles design, in amongst our permanent members of staff, and pretty much everyone in the middle, engineers and architects. And it gives us an amazing opportunity to do horizon scanning. And so this year we entered a team of students, a volunteer team of students from both Newcastle and Northumbria University into the Biodesign Challenge, which is an international competition for aspiring biodesigners, for people from a whole range of different design backgrounds who think that biology is the future of their fields of work. We entered a team that included designers from Northumbria, architects from Newcastle, and bioscientists actually from both institutions. And we entered our best competition, a project called Kalina, and on Friday we discovered that we'd won the top 6 project, and also we'd won the prize for outstanding presentation. You can watch the videos at the links here. There's really, really good, it was an amazing project that they did on the future of food and the built environment and dining and food security. It was a really holistic project. It's quite, in many ways, quite controversial. There are aspects of it that are deliberately polemic, but it was a really fascinating project, and it shows what we can do with the students now that we have at our disposal and the context that we can create for them. So that's it for me. I just my email is there. Please do follow our Twitter feed, and also if you're interested in more, our website is now live. So bbe.ac.uk is the hub website, and we're starting to update it all the time with news, and also it will give you a little bit of a profile of the people who are working with us as well, and some of the other themes. So thank you very much.
Thank you so much, Martyn. That was really, really brilliant. And personally, from my point of view, as someone that's quite new to this, I think kind of being able to see where different innovations are and what level those are at and kind of how they're starting to develop in different areas, I think has been really interesting. And I can't wait to visit the hub when it's open for visitors to be able to see some of this in real life as well. So thank you so much for kind of bringing us kind of through that journey as well with you. We've had a number of questions already come through on the Q&A chat for both you, Martyn, and Ehab. So we will get started with those now, if that's okay. We've got about just around 10 minutes or so to run through those questions before we finish for the morning. So Ehab, I'm just going to direct this kind of first one to you, and I think maybe Martyn, it might come in, you kind of come into play on this as well, because I think you talked about some of the scalability problems. But I suppose it kind of comes around as these products as they develop, and as you kind of take them from this kind of testing lab phase into kind of commercialization, and then also kind of, I suppose, to the mass market. Sometimes when these new products or sustainable products are being developed, they can have more of a premium product price range. So I suppose kind of what approach really are you taking to this from a Biome point of view? And I suppose, is there any other considerations maybe both of you been thinking around, I suppose, kind of that large cost that does exist around kind of taking, I suppose, something from the lab into kind of industrial manufacturing processes and then on to kind of the building site too?
Thank you, Emma. I think that's actually a very critical question. Just to put things into perspective, or to give some context, I started by developing Triagamy, the interlocking construction system, patented it and started developing it, and chose a few materials that I thought were perfect for it, and then very quickly realized that the costs associated with those materials were absolutely extortionate, or they were just at a research stage and not really scalable. And that was really the point at which we decided to pivot and develop materials that are affordable, that are scalable, and that at the scale of the construction industry will still have a positive and regenerative impact. So that is something that is really, really important to us. When working with living organisms and natural processes, there's a real sort of commercial or business benefit, because you're working with living organisms to do most of the work. So you're not using hard force, you're not using heavy machinery, and you don't actually need that much human intervention. So the costs of manufacturing are actually much lower when compared to conventional or traditional extractive processes. So at launch, which is towards the end of this year, our manufacturing facility is going to be operational around August. We're going to need a few months to calibrate things and ensure that everything is running appropriately. So by the end of the year, the material will be available at a price point of around 25 to 30 pounds per square meter. That's when we're producing 20 homes per month at the most, and 10 homes per month at a minimum. So at that tiny scale, compared to other materials that are available on the market, we're already competitive when it comes to price, when you look at all of the social and environmental benefits that we're offering. As we scale, we're going to bring that price point down to about 10 to 15 pounds per square meter, which is actually cheaper than anything that can perform the way our materials perform. Another consideration for scalability is the way that we're using waste streams or byproducts that are natural. It is very easy to have fields and fields growing of agricultural products that result in waste streams that we can use, but we've learned to say no to so many of these, because we don't want to create another problem by providing this solution. So we only use waste streams and byproducts that are a byproduct of an industrial process that is established, or the food industry, for example. And we take those byproducts and we select them based on how scalable they are themselves and what the trajectory of growth for them is in the future. So yeah, I think affordability and scalability is an absolutely critical issue when it comes to sustainability. It's always been perceived as a premium, and we are making sure that we're able to really transform that. Because we want it to be the mainstream. Our main market that we're looking at is social housing. So yeah.
Yeah, I think that's it. I think it's kind of, sustainability needs to become kind of business as usual. And if it's kind of being seen as a higher price point or not as cheap then, or not as affordable, then that is going to definitely be a difficulty in terms of it kind of getting accepted onto the large scale market as
Absolutely,
well.
absolutely.
So I think that's really important. And I think kind of alongside building up kind of, I suppose, the sustainability case for a lot of these new materials, which is really, really important, especially around kind of the ambitions and the legal requirement to hit net zero by 2050, is also, you know, we have to have strong kind of business models and business cases that are robust, that are going to be able to help us take these innovations to market. Did you have anything else that you maybe wanted to add to that point, Martyn, in terms of kind of where your guys are coming from in a much more earlier stage innovation and some of the lower TRL levels as well, and kind of pushing those through too?
Yeah, I suppose that there are, I mean, there's certainly scalability issues for us. I mean, the great thing, we work with microbes most of the time. So as I said before, they're 2 microns across. So you've got to then get that to something of the built environment scale. But that's done because we can have trillions of them very quickly. They self-assemble and they replicate. So actually, you just need a very big bioreactor quite often to get as much of any sort of material as you want. And of course, there are biotechnology at industrial scale for chemicals manufacturing and other things. This is fairly standard practice. It's interesting. I know less about the later TRL levels, and we're aware of the likely challenges to get some of these things to market if we can prove the case. To give one example would be cement manufacture, where, I mean, even if we can demonstrate, for example, a microbial cement, which is in theory as effective, as efficient to produce as a normal concrete would be, we have a world that is built around incredibly expensive infrastructure that is designed for concrete manufacture of a certain type. And there's going to be a lot of resistance to that level of change and a lot of inward investment to make those transformations. And so I think a lot of us are waiting for that tipping point where actually the cost of not doing these things for governments and for industry is much greater than the cost of doing these things. And I don't think we're there yet in some industries, particularly some of the foundational industries in the UK, where we've invested so heavily in old scale infrastructure. We're trying to make incremental changes to that to improve it. But there needs to be a kind of tipping point where the work that we're doing becomes more mainstream. And I think we just have to push, but also to wait for that to happen as well.
Yeah, I think that's exactly it. I think, you know, kind of decarbonization is so important. And you mentioned kind of concrete there being very kind of the embodied carbon within that particular material is so high. So we need to kind of, you know, explore where those other materials could come in. In terms of a question for you then, Martyn, and it's in regard to the thinking soil. Would you use the current design codes to design the foundation blocks, or would you envision a total new approach to the design? That comes from Brunella.
Yeah, so it's kind of interesting that, so I'll fess up and say that since we started the Thinking Soils project, we realized probably that the mechanical sensor that we're creating, this is not the best solution to building foundations. So I think that we would recognize, so we set it up as a moonshot. So for me, it was as a kind of hobby project to say, okay, so how can I get the synthetic biology knowledge that I know and the built environment knowledge that I know and bring it together in something that's really provocative, that sets an agenda. And so we applied on that basis for this research funding that pushed synthetic biology into territories that it's never been in before, and pushed the built environment into territories that it's never been in before. We hold it as a sort of model of the Moonshot project, really, that gets a group of people around a table collaborating who would never usually do it. Whether it's a good solution to building foundations or not, I think is another question. And I think the answer I would say is probably no. I think our mechanical sensor probably has some application in the medical field. I think it may well have applications in certain very highly engineered materials where you might imagine kind of all kinds of critical systems that require the kind of level of mechanical sensing you could get from a biological sensor that maybe you can't get from a more traditional digital sensor, or maybe where you need a robust solution that doesn't require energy and so on. So actually the way that we see that going could be very different from the built environment, but we started it from that position because I think Ehab's a great example of this as well. There's something about architectural designers or people from that, we're kind of fearless to just say, okay, well, what if? Can we do that? Could we have a go at that? And then what you do is you drive innovation through asking questions that nobody else is asking because no one thought to ask it. So I think that's our approach. I think the practicalities of Thinking Soils as a product, I think we're a long way from that, to be honest.
Yeah, but it's always kind of great to, I think it always kind of starts out in a great point, as you say, when you ask those questions, like, wouldn't it be great if, and then kind of start to explore some of those themes and see where it kind of takes you. And I think kind of, I suppose you've mentioned with Ehab, you started off in a much more different place around kind of the development of, you know, the products that you were looking into as part of Biome, and that's, you know, that's changed and evolved over time. But it's, you know, it's still kind of been that same kind of thinking point around how can nature inspire a new range of products. I'm just going to bundle together a couple of very quick fire questions for you, Ehab, if that's okay. One is around kind of, I suppose, the warranties and guarantees that you might propose for the products. One is around kind of, will bugs eat the building materials that are made from food waste? Very valid question. I actually remembered when I showed, I think it was, I showed this, that your particular material to Prince Charles, and he was just like, well, is it edible? And I was like, no, please don't try that. I don't want to be responsible. So, you know, hopefully humans don't eat it, but definitely not bugs. But yeah, will they be inclined to eat it? And I suppose there's a little bit as well around kind of LCA as well, kind of the life cycle assessment of the products you've developed too. So if you're able to kind of take those quite quickly.
Absolutely. Yeah, so you can think of the materials we're developing in a very similar way of how we use and think of wood. You know, we've got wood that's or timber that's used in building infrastructure for years and years, and we've learned to figure out ways of how to, you know, resist bioattack and things like that. With our materials, we use, again, the way that we evolve the strains. For example, we encourage strains to produce more chitin. And that makes it much more harder wearing and allows it to actually fight bioattack, because it's just much more difficult for those microbes to consume, so they don't bother wasting their energy on that. As well as that, also, we look at natural coatings and natural ways of protecting the material to allow it to last for longer. With the lifespan and the life cycle question, when we look at the entire life cycle of our materials, there's only a positive impact, and that's something that we've worked really hard to achieve. From a carbon perspective, from an energy perspective, fair enough, our first facility in West Somerset is not going to be solar powered. We can't really afford that to start with, but that's what we're working towards. And as soon as we're able, and as soon as we scale up, it will definitely be all completely renewable energy. But even the energy used, we've basically taken some machinery from the food industry, from the agriculture industry, put them together in a very DIY way that works really well, and allowed that to really reduce the energy intake from, instead of using off-the-shelf processes. So again, it's that sort of asking questions and taking a very innovative and creative approach to reduce the impact at every stage of the process. At the end of the material's life, it can either be cannibalized or fed back to the next batch of mycelium, because they are cannibals, or it can be decomposed or called compostable. When it's decomposed, it provides a pH balanced nutrition to the soils, and it's a completely natural process without any toxins or chemicals. So again, the impact is always only positive.
Great. Thank you. I think that's really comprehensive and covers all those different points. And I think it's really interesting. It's kind of that full kind of circular approach to make sure that, you know, whatever it is you're putting in there is definitely going to be able to be processed at the end. So we're not kind of having a detrimental impact as well at the end of the life. So it continues to have those kind of circular themes run throughout. So that's great. I think that's kind of all the time we have, unfortunately, this morning for questions. But there is some kind of in the Q&A box. So Martyn, Ehab, if you want to have a quick look at those, and if there's anything that you can answer really quickly, feel free to type an answer. Alternatively, I think Ehab and Martyn's details were available in their presentation. So if you do want to ask any questions or follow up the conversation with them, please do that. I am just going to follow up and finish with kind of just to take you through just kind of what we've got coming up. If I can just find my slides. I don't think they're here. Oh, here we go. Yes. So very not so smooth transition there, but we just kind of wanted to say that this webinar this morning was brought to you by the Nature Inspired Solutions Special Interest Group at the KTN. This group has been around for a year now, and we've got a really great community of organisations, academics and researchers that are really active in this space that are kind of coming together. It was launched last July, and we're really keen to kind of bring as many other organisations into the group as possible. The aims of the special interest group is really to kind of bring together a very diverse community that's looking at nature inspired across a number of different sectors, including transport, energy, and infrastructure. It's to really raise the profile of this industry and kind of the sector and space, and develop ideas for collaborative projects and identify unmet needs within these target industries. So we know that, you know, there's definitely specific challenges that need to be addressed within those, particularly around future mobility and around clean growth. Could nature-inspired solutions be one of those approaches or one of those methodologies that we could use? And by hopefully having a special interest group, we can bring together the key players to explore that even further. To allow us to do that, we also do have, as I mentioned, a webinar series running over the course of the summer. This was our very first session in this webinar series, and it's so great to see so many of you show up this morning. If you are interested in how nature-inspired solutions can have a role to play in other sectors, then please do join us. On the July 14th, we will be exploring its role in manufacturing. Then we'll be followed by looking at energy, and then finally our final session on August 28th, we'll be looking at nature-inspired solutions within future flight. We have a LinkedIn group. Join it or sign up to our newsletter on the website, where we'll be sharing all the details of these events that are coming up, and you are more than welcome to sign up to those. Finally, really great conversation today. Really want to say a huge thank you to my colleagues Pinham and George for helping me pull together everything on the session to get today, and all of the behind the scenes work that you haven't really seen, but they have been there doing a great job. Also, our amazing speakers, Martyn and Ehab, thank you so much for kind of taking us through and demonstrating what an amazing and inspirational way nature can play in transforming construction for the better. And if you would like to continue the conversation, then please sign up to Meet Mojo and join us again at 1:30, where you can connect to other organizations. There's been some really great organizations already put their details in the chat. Now is kind of the time to pick it up and speak to them on there. But yeah, thank you so much, and I hope you all enjoy the rest of your Tuesday, and we hope to see the next session on the 14th of July. Thank you.